Okay, so in this section, we're going to look at computing volumes of what are called solids of revolution. The two methods that we have are called disk and washers. They're actually the same method. Uh, Disk is a special case of the what are called washer methods. And so the idea is this. Let me paint the picture for you here. So what I have in this picture is just a graph of y equals x squared, right? The little purple graph. And what I've drawn is the inverse of that, the negative in front. So I've taken the purple graph and flipped it about the x-axis. And now what I want you to imagine here is that we have generated a solid shape, right, by taking the graph and rotating it so that we get this kind of three-dimensional horn shape, if you will. This three-dimensional horn shape, if you will, by taking the graph. And so we would like to compute the volume of this shape. Okay, so what we have is this little horn that's, again, three-dimensional. Okay, this three-dimensional shape that we've generated by, again, taking and rotating that shape so that we get this kind of horn shape that's bounded by the y equals x squared graph. So that's the shape we're dealing with there. That's the shape we're dealing with. We want to compute the volume of that. So we need to find a way to approximate it. And the idea is, well, if we were doing area, we used rectangles. So the idea here is, what if we take and make a rectangle here? And if we were looking at that rectangle right there, and we rotated that about the x-axis, that rectangle, then we would end up getting this shape, which is actually a cylinder. Okay, we would end up getting this shape here, which is actually a cylinder. Okay, where the radius of that cylinder is just the height of the function f of x. Right? And the height of that cylinder is our subdivision delta xi. So we end up generating this cylinder. We end up generating this cylinder here. And that's going to be our approximation step. Well, the volume of a cylinder from geometry is pi r squared h. So what we need to do is derive a formula now for doing the volume of this solid, or any solid. And so we're going to approach it from this visual picture here. And so step one is we subdivide. So we would take the whole x-axis between, in this case, 0 to 2 in this picture, divide it up into a bunch of little subintervals. And then here we are working with our ith subinterval. Okay, we're working with our ith subinterval right here. So we subdivide. Right, we're taking the height to be f of x I right here. Right, and we're going to compute the volume of that cylinder when we take that little rectangle and rotate it about. Right, rotate it about the x-axis. So using our volume formula there, we would get our approximation step. V sub I would be pi. The radius of our cylinder is actually the function f of xi squared, and then h is just our delta xi. Okay. So that would be our approximation step. Okay, we're then going to add all of those volumes up. So we're going to have the sum of all that stuff, pi f of xi squared delta xi. Right. We're then going to take the limit. The limit's going to transform this from a sum into an integral. And so the volume will be the integral between your two limits, a and b, of pi f of x I becomes f of x squared dx. And so now we have the formula for the volume of a disk. The volume of a disk. Okay. And so that's the derivation. That's the idea of the formula. We're just going to be using this little disk here and approximating it with a bunch of little disks. So that we get volume is just actually the integral from a to b of pi times the function squared dx. So we're going to take a look at this and see how this works in our upcoming examples here.